Hello, today I would like to show you how you can implement a the terms called swarm intelligence. This is a swarm intelligence is like an multi-agent system that each agent has its local rules to move around, and then when it gets to the crowd, it moves like as the crowd itself has its own intelligence, like the murmuration of the birds, like this. So there is a way to simulate this kind of murmurations in computer programming, and the method was developed by a Craig Raynolds called Boids. And basically he's making like simple rules for each agent, which is a Boid here. So the first rule is that in specific search areas for each agent, he or she looks at other agents inside a search radius, and if there is one nearby, then the agent will try to go away from those agents so that it will keep some certain distance between them. And there's another rules for this agent that in specific search areas, if the agents see other agents surrounding him, it will try to follow the way the way the other agents are facing to, and try to align with them to move as if he wants to move with them. And another rules for this agent is the opposite of separations. It's cohesion. In certain search areas, if the agent itself is a bit too far from other agents, then he'll try to go close to them so that it will make a crowd. So this kind of simple rules being applied to each agent, and then when you combine them all together, then it will make a pretty interesting computer simulated murmurations, which is called swarm intelligence. So I'll tell you how you could do that in Houdini, which is I think it's a great medium to try out this thing, besides other programming language, because you can try it in 3D. So let's do that. Okay, first of all, let's start from making a geometry and delete the file, and let's start from, let's say, null, to have all the parameters inside that you're gonna want to use for this scene. Okay, and then let's make some first geometry. Let's go with the sphere first. So the sphere itself will be the source of the initial position of the agents, in this case boys. So let's you make the sphere first, and then let's be able to control the radius of the sphere. So I'll make a radius init radius to set the size and keep the range from, could be 0 to 10, fine. and copy this to the radius. Okay, then let's use the ISO offset to convert this into volume, and I'll set the uniform sampling divisions to 50 to make the volume consistent. Okay, and then use the scatter to plot the points inside this volume, and let's make a parameter for this number of points inside this volume. So let's make an integer parameter here, num voids, and could be from 0 to 1000, could be more. And let's copy this parameter and paste it here for total count. Right. Okay. Now let's set some attributes to each points in order to calculate the next position inside the simulations using those rules that I show you here. So in order to move those stuff, the things that you need is the how fast it's moving, and the direction, and the search radius, I guess, and the maximum force and the maximum speed, so that it will reduce, it wouldn't go too fast. And let's apply that attributes here. So let's make a point or angle here. I'll just name this init, and first of all, velocity, I'm gonna use the random based on the points, and will be a let's make a calculations like this, and let's see how it looks like. So I have the velocity from -1 to 1 for each x and y and z of the velocity. So this will be the initial velocity, where it should, which direction it should go initially. Okay, and another one, acceleration. This will be used to accelerate the movements to modify the velocity on each frame, but for initially it could be 0. And the acceleration will be updated with the function like separation, alignments, and cohesion. So later on I will do it inside the solver. And let's make a search radius attributes. Let's start from point 2. Maybe I could parameterize this as well, so let's give a CHF search rad. Okay, and let's also make the parameter here as well. So I'm gonna name this search radius. Okay, and the range from 0 to 10, or I'll just do with the 0 to 1, because search radius shouldn't be too big because it's already pretty packed. Okay, so let's start from like 0.3, copy parameter and paste it here to link. Okay, and the next attribute will be max force. This could also be parameterized as well, so I'm gonna give a max force, another one a max speed, so I'm gonna give another parameter max speed. And finally, let's apply the ID to each points with the point number. Okay, so for the max force and max speed, I'm gonna make the same one here. Max force, max force, max speed, max speed. Alright, and the range for the max speed 0 to 1. For the max force, it shouldn't be too big, so I'm gonna set the maximum to 0.1. Okay, and then let's set the initial max force to be 0.1 and the max speed to be 0.5. Oh, for the max force 0.01. Okay, let's copy this and paste it here, and also paste it here, and rename this to speed. Okay, now let's check the attributes, point attributes. So there's ID, there's ACC, acceleration, there's max force, max speed, and the velocity and the radius. Okay, should be fine. Now let's make some let's set some group for the agents. So I'm gonna use a group to make all the points, initial points, to be agent. Okay, then here comes a solver to actually build the simulations. Okay, let's go inside the solver and try making all those functions one by one. I guess there's two ways to do it. One way is to use Python and just do it on one component. Or you can just separate the functions with the wrangles and just do each functions for each component. I mean the node. I mean you could also do it just using one node, one wrangle node, but it will be hard to debug. So what I'm gonna do is to use vex wrangle for each function, separate alignments and cohesion, and then combine them all together and with another wrangle to decide how each agent should move in the next frame. So let's do that. That's because if you use Python, it will be single threaded. I think it will be too slow to calculate. So that's why I'm gonna use wrangle. Okay, so I'm gonna bring the point wrangle and filter out the group to agent and the points. Okay, now let's also set the boundary of this geometry. How this flock of bird should move inside. So I'm gonna set the boundary like where the bird should move. Could be like the size of 50 for X, Y, and Z. Maybe for that one I could also parameterize as well. So I'm gonna make a float called bounds, and I'm gonna name this bound size. Okay, and let's go back to the controller and make the same parameter here. Bound size, and the range from 0 to shouldn't be 0, 1 to like 100 or 50 or maybe 100, and accept. Let's go with the 50, then copy this parameter and go back here, paste it here. Okay, so if the bounds is 50, then the radius of the box, I mean, I'm not sure if you call radius for our boxes, but the half size, it will be 25. So and I'm gonna check each point, whether the point is outside the box or whether inside the box. So let's check that out using the conditions. If the absolute value of at mark p.x equals to is more than bounds divided by 2, which is 25 in this case, if it's 50. So if it's outside the boundary, then set the velocity of the x to be -1. So this means is that if it's going outside on the x direction, then the reason why it's going outside is because the velocity is facing from center to the outward to the x direction. So what I should do is to multiply its velocity, the x value of the velocity, to -1, so that it will just go to the opposite direction like a reflection. So this is what it's doing, and gonna do the same thing for the y and z. So I'm gonna copy this, paste it 2 times, and change this to y, and for this one to be z. Okay, so this will be the bounding conditions. So I'm gonna name this boundary. So, but in order to use this thing, you first need to move the update the velocity. So this will be the last thing. And first thing I want to do is to implement this separate function. So let's do that. Okay, let's make a point wrangle again. Point wrangle. Set the group filter to agent, and okay. Since I already have some search radius set on the controller parameters, I think I'm gonna use this for the separation radius. So so it's like this. The search radius for this agent for the separation will be used to check if the agent is within the other agents is within this search areas, and then if the agents are inside this area, then check check its positions and make a separation vectors in order to move this void. Okay, so I'm gonna name this sep as a separations and make a dsep as a separation distance. So sep dist and as I said, something chf. Am I seeing anything? Nope. Seems like it's not making anything. I'll try again. dsep equals chf dsep. Okay, and let's link this with the search radius here. Could be like maybe it's too small for this one. I'll set the search radius range from to be 0 to 10, and well, actually I think I need like 3 types of radiuses. One for the separations, one for the alignments, and one for the cohesion. So having just one might not be enough. I'm gonna make 2 more. Okay, so I'm gonna rename this to sep radius for the first one, and then cohesion radius. And also a alignment radius. And all be the range be 0 to 10. Okay. And let's go back to the init wrangle, and I'm gonna just comment out this search radius. I'm not gonna make it inside attributes. I'm just gonna access into the controller's parameters. So I'm gonna set the separation radius to something like 2, and cohesion radius to be something like 5, and alignment radius something like 5 as well. So let's copy this, go back to the solver and go to the separations, and for the separation distance I'm gonna copy this separation radius. Okay, now here comes the coding for the separations. Basically all separation, cohesion or alignment looks pretty much the same, pretty similar. It's just the small differences. So once you make separation, it will be easier for you to make both cohesion or alignment. So the first thing, let's make a variable of vector called steer, and use this to define where it should move, and also make a count, and make a for loop to access all the points inside in the first node, first input. So this. And what I want to check is that for each point inside a point wrangle, you want to check other agents, other points. So make a condition like if the pt num is not I, which means you're looking at the different agents for inside a for loop. Let's make a another position of the point. So I'm gonna say pp pos point at I, and let's get the distance between the current point plus the other agents with the distance function. And here I'm gonna make a condition for the separations. If d is larger than 0, it should always be larger than 0, I guess. And d is less than d sep, which means the other agents is within this search radius. So I'm looking at those blue agents inside this diagram. Then make a vector called diff, which is a vector which goes from the blue agents to the green agent, which are the current point on the point wrangle. So I'm making the vector from the blue to green, the blue to green, the blue to green for each agents. And and since you don't know how much agents you're gonna have inside this for loops, so I'm gonna have to add all the vectors together. So in order to do that, let's first normalize this vector, the direction vector, using the normalize function. Then apply some multiply or divide with the distance, so that the strength of the separations will be affected by the how far it's been, or how close it's to the agents, how close is the other agents to the current agents. So if it's really close, then the vector, the strength, the magnitude of the vector will be pretty strong. If it's pretty far away, then it will be less strong, less influence. And last of all, add this diff vector to the steer and count up. Okay, so the reason why I'm using count is that I wanted to check if there's more than one another vectors which is inside its search areas. So if the count is larger than 0, means that the point has at least one neighbors within the search radius. In that case, divide this steer by the number of count. This is also a normalizing method, so that the steer shouldn't be too big, won't be too big, or have the correct direction. Okay. And if let's make another condition. If the length of the steer is larger than 0, So if the steer vector has the amount of value more than 0, which means the vector, which means the agents should move, then first of all, let's normalize the steer vector, and then multiply this steer by a max speed, which should be inside this attributes for the point. So there's max speed, yeah. And also subdivide steer with the current velocity which point has, so that the current velocity will be used somehow with the steer, so that the point wouldn't like go too drastic, but be keeping the current velocity somehow like this. And if the length of the steer is more than F max force, in this case, if it's too, the speed is too strong, the speed is too fast, then normalize again this steer, and multiply this with the max force. Okay. Now it should be good for the separation. I think I'm missing. Okay. So this will be the separation function. And for each frame, using the solver, it will update the steer thing. And this, by updating the steer, finally you have to update the ACC acceleration with the steer to use it as acceleration value. So the ACC plus steer, and it could all be like this, but you could also multiply this with some value here, and this could also be a parameter to give how influential separation should be compared to other cohesion and alignments. So this is more like a ratio between cohesion and other functions. So let's also parameterize this as well. So float sep strength or sep force, and use this sep force to here. And let's also make a sep force inside the controller to give the ratio. So I'm gonna make 3 of them for the separation, cohesion, alignment. Sep ratio, sep ratio, or sep strength might be better. Strength from 0 to 10 should be fine, and make another one, and cohesion strengths, and alignment strength. Right. Okay, apply. Separation strength to be, let's say it will be 1.5, and the alignment strength be something like 1.0, and the cohesion will be 1.0 again. After making all those network, we could see how these value will differentiate how agents moves. Okay, let's copy this parameter and go back and paste it here. Right. Now that should be all for the separations. I'm gonna go with the alignment and the cohesion. So basically it will be pretty much similar. So I'm gonna copy the separations 2 times and connect to later on, and rename this align, and then cohesion. Now let's go with the alignment. Okay. Well, I have to rename these things to not the decept, but the alignment. So the align, and well, maybe in order to use all these with the same parameters, maybe it will be better to use the common name for the distance and the separation force. I mean the ratios. Okay, I'm just gonna delete this and go back to the separation and rename this to dist. I'm gonna say neighbor distance as and dist, and for the force I'm gonna say just gonna say force ratio, F ratio. Okay, and I gotta replace this with ndist, and this one to be force ratio. Then just copy this to here and copy this to here, and let's remove this dcep and sepf, which I don't use anymore. Okay, should be good, and then it will be much more easy to use this as a template. Okay, copy this, name this align again, this to be cohesion. Okay, for the alignment I'm gonna have to use the different wait a minute. I think I'm not having the same one yet. Interesting. I'm gonna copy this and paste it again. Okay, maybe I forgot to copy this. Okay, go back to the line, and first of all I have to change the type of parameters here. It's not the separation radius now, it will be the alignment radius, and for this one it's not the separation strength, but it will be the alignment strength. Okay, Now let's go back. We have this endist, F ratio, and count and steer. For the alignment, I would also like to make another variable called vector sum. Okay, and basically all I'm doing in this for loop, pretty much the same for first few lines. This one is okay. This is okay because it's checking whether the point is inside this search areas, and this will be different. Okay, so in this case, I'm gonna use the sum. So sum will be added with the velocity of this point. So I'm gonna add all other agents' velocity. So in this case, this one. So if, let's say in the point rank where you're looking at this agent, and you have you're checking all the agents inside the search radius, as in this conditions, and then you will know each agent's velocity, which is this blue line. So first thing I would like to do is to add all these blue lines to see the average direction each agent has. So let's do that. So that's the reason why I'm using sum, to add up all the velocity from those agents. I'm gonna use the point function to access the velocity at the I number. And that's the first thing that I will do. And if the count is more than 0, which means you have more than one neighbor agents, I'm gonna average this sum vector with the number of count, and then normalize, which means set the length of the vector to be 1, and then multiply this with the max speed, as I did with the separation function. So I guess I could just copy these. And instead of using steer, I'm gonna use sum. Oh, but yeah. After multiplying this sum with the max speed, what I'm gonna do now is that I'm gonna update this steer from here. What I want to do is not subtracting sum with the velocity, but make a new steer velocity, which will be a subtraction with the sum subtracted by velocity, which could also mean the same meaning as using the sum to be subtracted with the velocity, but I'll go with this way. And the checking will be the same as the separation, then the steer will be normalized, and then multiply with the max force, so they'll be the same. Okay, and there's also a condition whether when the count is equals to 0. So in that case, I'm gonna set this steer to be 0. I might not need this function at all because I'm already initializing the steer vectors up here, so might not need this. Just in case I'm writing this. And I don't need those. Okay, and what else? Oh yeah. And now that I have the initial, the updated steer vector from this sum vector, now I think I shouldn't have deleted this one because I'm still gonna have to use this to set the maximum speed of the steer. So here comes the similar function as I did for the separations. Check the length of the steer, whether it's larger than 0, and normalize this. Multiply by max speed and steer subtracted by velocity. And then check if the steer's length is larger than max force. Then if so, normalize this steer again, then multiply it by max force. And then finally add this steer to the acceleration with the F ratio, and they'll be the same as well. So pretty much the same. And then let's go to the cohesion. This for the cohesion, it's basically what I'm gonna do is to just do the opposite of separations. The separations try to go away from these agents, but for the cohesion, try to go close to the other agents, the nearby agents. So it's pretty much the same, just some value will be opposite. Okay, so first of all, let's link the correct parameters. So I'm gonna rename this cohesion radius and the cohesion strengths. Check whether if okay, I'm not getting the value here because I have mislabeled it. Okay, should be good. The parameter has been linked. The next thing we'll do is for this one, let's also make the sum as well. And for these conditions, let's look at where we should change. And I guess it's inside here again. Let's delete those. And so I have this condition if the distance is whether the other neighbors is within the search radius. And this time I don't need these differences, but what I want to do here now is to check all the point position of the search for the nearby agents. So wanna sum up all the position of the points for these blue ones. So I'm gonna sum up using the sum vectors and just add those point position of the neighbors to the sum. Now I'm gonna check all the count, all the point position. I'm gonna check the count, whether if there's any neighbors within the search radius with the count. If it's more than 0, it will be at least one neighbors. So we'll do the same, average the point position of the sum with the count, number of count, and then make a desired vector, which will be sum subtracted by the current position of the point, and make that desired vector normalized. And then multiply it with the max speed. And then make a steer, desired subtracted by velocity, current velocity, and if the length of the steer is larger than the max force, then steer should be the size of the steer should be same as the max force. So normalize this first and multiply it with the max force. And as I did for the alignment, if the count is 0, then set the steer to 0. Okay, and finally probably do all the same things that I did for the alignment and the separations. This one should all be the same, and then this will be the same as well. Now until here we have updated the acceleration 3 times using different functions, and we should see some changes in the acceleration here. Okay, now the final things that I have to do is to use these acceleration value to actually update the velocity, so that to use it to move the point. So let's do that. I'm gonna make another point wrangle before the boundary. Point wrangle. I'm gonna name this update. And the things that I'm gonna do is to, first of all, let's access to the agent points, and then add the acceleration to the velocity, but in this case velocity will be faster and faster for each frame, so I have to reduce the speed somehow. And this is where comes the max speed. If the length of the v velocity is larger than max speed, then velocity should be the same size as max speed. Okay. And finally, apply this velocity to the point position so that the point will be moved. And update the ACC to 0. Because for next frame it's gonna be updated again with the new value. And then let's set the normal, which is the direction of the facing of the points, to be the same as the velocity. Alright, so let's check the normal, and it's facing pretty randomly right now, but it's okay. Okay, and that should be all for the solver calculations. Basically the hard part, the core part of the simulations should be done with these setups. And let's check the flag to the boundary, and then go back to the geometry, and let's just visualize the normal and then try to play at this point. And if you look from far away, yeah, you can see that oh, it's too fast. You can see that if it's pretty much close to each other, the agents will try to like gather all together to move in the same direction, and if it's too close, it's try to separate. And I think I can control these behaviors using those parameters that I set. For example, if you want to set the cohesion radius higher, then there's more chance that other agents find the nearby one. So let's add this to like 8, and more agents will be able to find each other again. Let's set to 10, and yeah, more like got more massive. But if it's like less than 5, like 3, the agent will be hard to find the nearby one less, so the mass will be smaller. And you could also control like the strengths of the separations or the cohesions. If I set the separation strengths to something like 5, the agents will try to separate with the higher velocity, will try to keep the distance much farther than the last time. So there's many ways to control this behaviors of each voice using those parameters. And if you look close to right now, the vector length is a bit too small. I'm gonna visualize this normal, scale up this normal a bit more, and see how each velocity is facing. And you can see that the velocity, points, is somehow aligning to each other if it's close enough. That's where alignment comes out, to control all these alignments. Pretty interesting, yeah? Now, this itself is pretty much done, but I would like to set additional nodes to visualize this to a bit more interesting shapes. a bit more interesting geometries. So I'm gonna use the trail to trail all the points, and maybe for these one, the trail lengths and the trail increments could be parameterized as well. I'm gonna hard code first, like 8 and 10, and then let's see how it goes. Now you have tons of points right now using the trail, and what I would like to do with this massive points is that I would like to connect all those points together to make trail lines. So let's see the parameters here. What I can use to connect all these points, which was born from the same points. I think I could use this ID to connect the points. So the points which has same ID should be should be the trailed out points, which should belongs to the same trails. So let's use the add component, add node, to give the line to this ID attributes. So polygon by group by attributes, the attribute name to be ID, and here I have those lines. And yeah, looks pretty interesting. Yeah. Now as you can see, it's a bit too blocky here. So I'm gonna smooth this out. I would like to smooth this out. And before doing that, I would like to make a primitive wrangle to control each lines, and to give a attributes to each points to use it to colorize each points on the trail and give a size for the polywires. So primitive wrangle. How should I name this? Trail at, and for each primitive you have a bunch of points which have same IDs. So I'm gonna access it using prim points, prim num, and make a for loop to this point, and access it using BTS from the BTS, and let's give a value which is from 0 to 1 using the I. So the value will be I divided by float length PTS minus 1. Should give a value from 0 to 1 based on the I value. Okay, and set that value to point attribute, first color, and also would like to make a p scale value. So from this p scale, from this value, I'm gonna would like to somehow use it for the size of the poly wires. So, and I would like to be able to control the shape of the trail as well. So I'm gonna make a new parameter to the controller with the ramp. I'm gonna name this shape ramp, or just the shape would be fine, I guess. And accept. I'm gonna set to the iterate interpolation to the B spline for both ends, and then add some points to give some interesting shape like this. Could be any shape. Okay. Now I would like to access this ramp using the value that I made inside a point primitive wrangle. So the float pskip value equals to ch ramp controller shape, and then I'm gonna convert 1 minus val with this ramp, and then set point attriv to this p scale of this point with this p scale val. Now let's see geometry spreadsheet. If I have colors, nope, I don't see any color value here. What about p scale? Nope. Okay, something is wrong. Something is wrong. So I got the point primitive. Oh no. Point prim number, prim points, and then let's see if I got this at least. Okay, at least I got this. I got this. And the value. Okay, the for loop looks okay, and PT accessing PTSI, okay, looks okay. Now this one might be wrong. I divided by float length of PTS minus 1. Should I make it my 1.0? And then set point attriv, the color attributes. Looks pretty okay to me. Oh yeah, I do have some changes here. Oh yeah, there was nothing wrong. And the P scale, yeah, I do see some changes here. So everything was okay. Alright, now that I have those values, I could now let's just do the resampling to smooth this out. Gonna check the, wow, it's too much. Could be like 1, and not the straight edges but subdivided edges will be make it smoother. Awesome. Yeah. Now let's see without showing the points how it looks like. Well, the iterations could be smaller, I guess. So I'm gonna set the trail length to be 5, I guess. Yeah, maybe 8 is fine. Okay. Now, after resampling it, I am going to use the polywire. And use the P scale to control this wire radius. I'm gonna access to the point attributes using the point expressions. P scale. Wait, what was the second input? Float. Okay. PT P scale 0. Would that be correct? Doesn't seem like so. Oh yeah, I do have it. Oh wow. It's a bit hard to see because it's the normal is a bit weird. I'm gonna just use a normal node here. Normal. Okay, looks much better. Yeah, already the geometry looks pretty cool. And then let's colorize this as well. Let's look at the point attribute, and if I have the color value still exist, yes, then I will use the color node. And use the point and use the ramp from attribute and use the call attribute, and then just set any color you want to set. This will be the which way? This will be the tip of the points, the last point that's been made, that's been moved. So I'm gonna set it to something like red and orange and bring the white to the left, and voila. Looks like a fish. And let's see how it looks. Cool. I'm gonna make a flipbook at this point, so I'm gonna pause this a little bit and show you how it's gonna be look like when it's rendered. Okay, I'm gonna pause it. Okay, it's done. Let's play. Let's see how it goes. Yeah, awesome. Looks pretty good. So this is the Swarm Intelligence, how you can implement the flocking code using Houdini. And you could also add like several types of agents all together and combine all these agents with the current agents so that you could make something like the prey and predators and that kind of type of situations as well. So the method itself is pretty fun to explore further. If you're interested, maybe I could make more of it using different types of agents. Okay, so that's it. Thank you very much.